Loud. And just remember, I have other videos that do cover this same material. So if this doesn't work as well as we would like, we will we'll move on from there. Okay, so we've talked about my motion. So if I had a spring that goes like this, and we allow that spring to bounce back and forth, that's what we call simple harmonic motion. And we said that I could tell my position at any time by looking at the amplitude cosine of my angular frequency times time, where my angular frequency is 2 pi times the frequency. And what we were saying is that this was going up and down and up and down and up and down. And this would be our amplitude, or this is our amplitude. And this represents our cosine wave. And we said that my cosine of anything is going to equal the sine plus x plus 90 degrees. So the sine and the cosine, I could use either of those items. I don't have to be focused on one or the other. I can use either. And we've chosen to use our cosine, right? And the amplitude goes from here. So if I'm thinking of a water wave, a wave that's on water, I would say that if this is from the crest of the wave, and this is the trough of the wave, the amplitude is going to equal 1/2 the distance between the crest minus the trough. So if this is where 5 and this is 3, the distance between the crest and the trough is 2. And so my amplitude would end up being 1. So we have that. Now, this wave, the way I'm writing this wave is an up and down. So think of a string, and I'm sending a pulse down my string. We're going to see this going up and down. And this is referred to as a transverse wave. So if I'm shaking a string, I'm going to get that up and down, up and down, up and down motion. So my simple harmonic motion, I can describe it as a wave that looks like this, but I can also describe a wave in a string, like a violin string or a guitar string or something like that. I could also describe that string as a pulse moving down the string, but it's also going to go down the string in a transverse fashion that looks like this. So transverse waves, I can represent by a string, or I can represent it with a slinky, shaking my slinky up and down. Now we also have a different type of a wave, and we call it a longitudinal wave. And we also can use a slinky to describe it. But if I take a spring and it gets compression and then it extends out and then it gets compression and then it extends out and then it gets compression and it extends out, this is a longitudinal wave because my things are vibrating back and forth. I can still describe it with a sine wave, but things are kind of doing this as it goes down the wave. All right, so slinky, it's an easy way to see it. You can also think about it as if I have a tuning fork, and my tuning fork is vibrating, And as it vibrates, it's going to compress and then it's going to open up and it's going to compress and it's going to open up and it's going to compress and it's going to open up. So we call this rarefication. And we call this compression. So I get rarefication and I get compression, and that works out really, really well for me. And this gives me my idea as we lead into sound, because that's exactly what's happening with sound. If you think of a speaker, the magnet in the speaker is going back and forth, and the speaker is actually sending a pulse through the air. And as the air moves, you can even feel it, right? And this morning, if you went out in the wind, you can feel it because air has mass to it. And as that wind blows, it's going to really slam into you. And if we were to have an explosion and that sound from the explosion moves out, we're going to feel that compression of the air. We're going to feel how that moves, and we're going to see that. Well, that's what's happening with sound. And my speaker is causing that to move back and forth, move back and forth, move back and forth. So that's one of the things that's happening is I'm getting that compression and rarefication, compression and rarefication, compression and rarefication. And where we are is that I can have a transverse or a longitudinal wave. Now, these both waves, if we're talking about a wave through a string, we're talking about a wave in the air, we're talking about a wave through water, those are all mechanical waves. So when we're talking about moving from our simple harmonic motion, it's describing this wave as we go through and we talk about things, but all of these mechanical waves have to have a medium. It's got to have something to transfer through. Air, the wood in your desk. If I'm thinking about an earthquake, right? Or an earthquake, all of a sudden we get a jolt inside the Earth's mantle, and all of a sudden that goes out. I'm going to get a compression, rarefication, compression, rarefication. I'm going to get a longitudinal wave. I can also see transverse waves. I can have a transverse wave in an earthquake. And those are the difference. We call them S and Ps. And that's from an earth science point of view. We can see that mechanical wave come through. A few years ago, when we had that 5.0 earthquake that happened on a Saturday morning, I had a lot of bird hunters that were out, and they said they actually saw the fence lines rotate or go up and down as the wave came through. They actually saw that nice transverse wave in the fence line, and they could actually see it. But we feel it as well. You know, we feel it, and we're going to feel it through our feet, and we're going to get that wave through our feet. Trains on a rail track are going to give us that kind of a transverse or a longitudinal wave through the metal. But mechanical waves have to have a medium. They have to have a medium, because one of the things that we know as we start dealing with sound, I gotta find my eraser here. As we start dealing with sound, is that sound is a mechanical wave, and it's got to have a medium. And we've all seen the video somewhere along the line. We have a classic alarm clock, right? And it's ringing, and we're getting that vibration, and it's ringing. And then I put it in a bell jar, and we pull a vacuum. And as we get the vacuum gets smaller and smaller, the sound becomes less and less. Sound has to have a medium in order to travel. Light, on the other hand, can travel through a vacuum. So light is a different kind of wave, and we'll come back to that at the end of the semester. But light is a different kind of wave than what we normally would see with a mechanical wave. So mechanical waves have to have a medium. Mechanical waves they can be longitudinal or transverse. Sound waves are going to be longitudinal as we move into that, but we can still describe it with our equations of motion that we were using for our simple harmonic motion. So let's take a clock. So we have a clock, and we've got the second hand ticking around the clock. So that would be an example of simple harmonic motion. It goes through a complete cycle and continues to go through those cycles, and it repeats that cycle over and over again. We can describe our tip of our item with a equation. My position of this equation, if I look at my position at any time, I'm going to talk about the amplitude. The amplitude, if I'm using the unit circle model, if I'm using that unit circle model for simple harmonic motion, remember we have 3 models for simple harmonic motion. We have our spring model that bounces up and down. We have our pendulum model that swings back and forth. And we have our circle model, the unit circle model, which allows it to go around in the circle, which gives us that angular velocity or that angular frequency, or our frequency as we go around. We've got that here. So my position is going to be the amplitude. And if I'm using the circle, that's just the radius or the length of my second hand. We know that the period, if it's a second, if we've got a second, the time that it takes for this to go around is 1 second. And that's my period. Remember, the period is the time that it takes to do a complete cycle. So in this case, if I'm following the second hand, it's going to go around in 1 second. When my frequency is equal to 1 over the period, which now is going to be 1 over 1, which now is 1 over 1 second minus, or this is equal to 1 hertz. Okay? Because the inverse of seconds is a hertz. So I now have my frequency. And if I'm writing this equation, this is cosine. And remember, we're going to do omega. Omega is equal to 2 pi times the frequency. So now we know the frequency is 1. So this is 2 pi times t. And now I have written that equation of motion, or my position equation, for my minute hand, or my second hand, because we're using a second hand here. So I can actually do that part just like that. So we can work with that piece. So we've got that. That's really kind of cool. We've got that. We can play with that. We also said that the velocity was going to equal a omega sine 2 pi times the frequency times time. So now we've got that piece of the puzzle. And then we can also do our acceleration is minus a omega squared cosine 2 pi times time. And so now I can write down, I can look at the tip of my second hand at any time and be able to write down its position, its velocity, and its acceleration. So we've looked at that model again. But that gives us our wave, kind of our wave functions that we're going to start moving into by looking at our sound. So let's talk through that a little bit. Let's talk a little bit about waves. So if I take a string and I send down a pulse. So I've got this pulse moving down a string. So we've got our string and we do the jerk and we get the pulse to go ahead and move down. We now not only have, if I look at each individual point on my string, what's happening? Well, this point is moving up and down as that pulse goes through the string. So as I'm going in here, this pulse is moving up and down. So I can describe the up and down motion of that pulse using my simple harmonic motion. That's how waves and simple harmonic motion are tied together. As this pulse moves, any individual piece of my string is going up and down. So think about it, if I'm in the water and I have my waves coming through in the water, here comes my wave, it's coming in, and now I have a buoy, and my buoy is tethered to the ground or tethered to the bottom here. It can't go in, it can't go left or right, it can only go up and down. So as this wave comes in, guess what this is doing? It's bobbing up and down as that wave passes. So my wave is moving. So my wave can move in an X direction, and my wave can move with respect to time. So I can have both time and position coming in. And on Wednesday, we'll talk about that a little bit. We'll get in here. In fact, let me see if I've got it right now. Okay. Da, 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 da. No, it comes in a little later. We'll get that in just a little bit. But I will have a position and a time component for my wave. So we do have that. Now, if I want to know about the speed of this wave, so velocity, remember velocity or speed. Velocity is a vector, so it has direction and magnitude. Speed is just the magnitude. And if we're thinking about my wave moving down my string, it's going to equal the wave length. We're now talking about how far apart are these things. We're talking about our wavelength. So if I'm looking at my item here, the time that it takes to go from there to there, from crest to crest, that's our period. But the distance from here to here is our wavelength. Okay? So the distance of our full wave is the wavelength. And that's going to be really interesting when we get to standing waves. Okay, we'll actually conceptually talk about standing waves right now, but we'll get to the standing waves. So depending on whether I'm looking at position as this wave is going through, I can be looking at that, or I can be looking at the distance. But my velocity is going to be my distance times my frequency. Let's look at the units. So if I'm at my units, I got meters and I have 1/seconds. I get meters per second. Check that out. I now have units of velocity. So my velocity of my wave as it's traveling through the medium is going to be just the frequency times my wavelength. So I can get that. So that's kind of an interesting one. If you haven't played with stuff, let's kind of look at a frequency and a wave. Let's kind of look at that. If I have a radio wave, and we're going to use KOSU, right? We use KOSU. KOSU says it's 99.1 on the FM dial. FM means frequency modulated, by the way, but radio waves are in megahertz. So if I'm going to my dial, I'm going to have a wave in megahertz. So KOSU is 99.1 megahertz. So this is going to be 99.1 times 10 to the 6 hertz. That's the frequency of the wave. That's the frequency that we have. Now, a radio wave is a light wave or an electromagnetic wave. And electromagnetic waves travel at the speed of light, which is 3 times 10 to the 8 meters per second. That's my speed of light. We'll talk about what the speed of sound is in just a second, but the speed of light is 3 times 10 to the 8 meters per second. I can calculate the wavelength. So what is the wavelength of the wave that's coming out of the KOSU station? Well, we say that my velocity is equal to the wavelength times the frequency. We know what the frequency is, so my velocity divided by the frequency is going to equal the wavelength. My velocity is 3 times 10 to the 8th meters per second. My frequency is 99.1 times 10 to the 6th, and I'm in 1/second. So my seconds are going to cancel out. This is really great. Okay, that's really great. And because when we get talking about decibels next week, when we talk about the intensity of sound next week, and we talk about the Doppler effect next week, I want to show you a couple of things, because as we move into working in physics 2, we're going to see some things about exponents. So just as a reminder about exponents, if I have 10 to the 8th times 10 to the 4th, this is going to end up being 10 to the 8 plus 4. So this is going to end up being 10 to the 12th. That's going to end up being 10 to the 12th. So we have that. And only 10 to the 12th. Or if I have 10 to the 8th divided by 10 to the 4th, that's going to equal 10, 8 minus 4, which is going to be equal to 10 to the 4th. Now, if I'm doing numbers like this, okay, if I'm doing numbers like that, it's going to be 3 divided by 990 or 99.1, and I have those pieces there. You can look in the appendix of your book, and it reminds you of how to deal with our exponents. Because we're going to start dealing with, and this is one of the challenges of physics 2, we deal with big numbers or we deal with a lot of little numbers. And we're using this notation a lot. And in the old days, when we didn't have these, we didn't have calculators that dealt with exponents, we had to do this in order to simplify our multiplication and division so that we didn't have to carry out a whole bunch of big numbers. So you've got that part there. So just as a reminder on how to do that. So if I take this equation, I'm going to get 3 divided by 99.1 times 10 to the 2nd, because of 8 minus 6 is 2. So now all I got to do is plug into my calculator. I don't have to plug in that whole thing. I don't have to use my exponent key. I don't have to do any of that. I get 3. Oops, Claire. I get 3 divided by 99.1, and I get 0.03027 times 10 to the 2nd. And if I do that, this is going to equal 3.03 meters. So we actually were able to calculate the length of the radio wave that's coming through. Couple of things, just as a reminder, not sure that people remember, haven't dealt with it. When you're writing this number or this number into WebAssign, let's say I want to write this number into WebAssign, I would write it into WebAssign as 0.3027 e to the 2. That's how I put it into WebAssign in WebAssign's notation, just as a quick reminder on that. So we have those things to look at our radio wave, so we can actually do that calculation. Well, let's talk about what affects the speed of a wave in a medium. So if I take my string here, and it's going through the pulse, so my pulse is moving this way, we can look at my string, and each little increment of my string has a mass. All right? Each little increment of my string has a mass. And we also know that I have a tension. How tight am I pulling this string? Think about a guitar string or a piano string. So I have 2 ends of my string, and if I have something that looks like that, it's very loose, we know we're not going to get a good vibration in here. I can still send a pulse down that string, but it's not going to go very far because it's not going to give me a really good idea as to how that works. Trying to get there. And I'm not finding it in here as quickly as I would want. But basically, we're dealing with the elastic property and its other property that has it go through here. And if I'm dealing with a string, the velocity is going to equal the tension in the string divided by what we call mu, and mu is what we call the linear density. So mu is equal to my linear density. And that is my mass per unit length. And this, I can also write this as the force divided by mu. And essentially what we're looking at is we're looking at the elastic property versus the inelastic property, which is allowing me to get to my velocity. Now, this is for a string. Now, if I'm dealing with that in air, or I'm dealing with that in wood, or I'm dealing with that with the Earth's crust, I'm going to get a similar equation because I'm looking at that elastic versus inelastic property, and I'm going to look at how fast that wave travels. Since we're talking about our strings and we're looking at it, if I take a string and I set up what we call a standing wave, okay? And a standing wave, we've seen them before because we've seen images of these before. We look at, and I get something that looks like that. We get a vibration that gets a standing wave. And we're going to ultimately call those harmonics. Okay, so I'm thinking a wave in a string, a wave in a pipe. We're going to get a wave in harmonics. And I can set up standing waves, and that's where I'm going to get constructive interference. So we've all seen, if I drop a pebble into a pond, we see that pebble into the pond send out a radial wave. It's going to go away from where I dropped it. If I drop another one over here, I'm going to get a similar situation. And we start to see what we call an interference pattern. Waves carry energy. I can send that pulse down the wave, but I can also send a pulse. So these two pulses are going to be coming at each other. And as they do that, what happens is as I get closer, I'm going to get something that looks like that. And eventually I'll get something that looks, I'll have them both on top of each other, but they'll be twice the height of each individual wave. Because I can get constructive or destructive interference. So I get these interference patterns, and we've seen these interference patterns. We actually use this to our advantage. A lot of you have noise canceling headsets or noise canceling earmuffs, because what we're trying to do is set up so that we're going to get constructive or destructive interference so that we can get these waves to cancel each other out. So I can add the waves, and the waves will continue to go out in their normal fashion. So what happens with my constructive interference, so let's say I have a wave that looks like this, and it's going to interact with a wave that looks like this. So these are coming together. I'm going to get constructive interference. So at some point, I'm going to get a wave that's twice the height, and that's constructive. They're going to add together. They're going to get bigger. But I can also have a wave that looks, it's going to interact with a wave that looks like this. This wave is going to come in. This wave is going to come in. And I'm going to get a wave at some point that looks like this. This is destructive. So I'm going to get constructive and destructive interference, and my waves will add together, which is kind of interesting because you can do this with signals. So those of you who play with any kind of recordings, or you're playing with oscilloscopes or things like that, I can send a wave pulse And what's going to be fun is if I send a square wave out and I'm sending a curved wave here and I get distracted and this wave's going this way and this wave's going this way. As this comes together, see if I can draw this. I'm going to get a wave that's going to start looking like that. Okay? Because I'm going to get constructive interference and these are going to start adding together and they're going to change. But ultimately, what will happen is this wave will come out in its normal shape and this wave will come out in its normal shape. So we'll see those waves. They'll end up here with the constructive interference and look weird for a little bit. But as we move through, the integrity of that pulse is going to remain the same unless we get dampening. And dampening, it's always, dampening is like friction, and we'll get some of that dampening. So back to our standing waves.
After the destructive wave, do those waves continue?
Do it. Say that again.
After the destructive waves, is that cancel out the wave or do they keep moving past?
They'll keep moving past too. So what'll happen there? So that's a great question. We'll keep going there. And so let's start with this. So if they come in like this, I'll get a spot where it's going to be like that, but then I'll ultimately get a spot where this will go that way and that will go that way. So after they've interacted with each other, they're going to do the same thing. So great question, because that gives me a chance to visualize it there. Thanks. Wonderful. It was just odd. All of a sudden I had a voice from over here instead of the computer. It's great because I'm in a room. Yeah, it's great. So that gives us our idea. So let's go back to standing waves. Any other questions so far? Because we're talking a lot of concepts right now. We're not putting the math to it yet. We'll put the math to it next week. Okay, so let's look at our standing waves. So we're going to talk about standing waves. And like I said, we've all seen these pictures, right? We've all seen these pictures. And the first time, if I do a standing wave and it looks like this is called the first harmonic. Okay, that's called the first harmonic. This right here is called a node. And this is called an antinode. All right. That's called a node and an antinode. Now, if you're looking at this, remember, a standing wave is a whole bunch of waves added together. So we're getting constructive interference, and we're getting it to a point that we're setting up this node on both ends, and we're going through here. This turns out to only be half a wavelength. Because remember, my wave looks like that. So I'm only looking at half. Now, granted, I'm looking at half of a whole bunch of them in order to get that standing wave set up, but I'm looking at only half. So this first harmonic this is a fixed point, and this is a fixed point. I've got those fixed points showing my nodes, and then I've got my antinodes, and that's my first harmonic. My second harmonic is going to be my standing wave. That now it looks like this. And so now I have one complete wavelength. The distance between here to here is one complete wavelength, and that's going to be my second harmonic. So when we start our standing waves, we're going to be able to set up our nodes and our antinodes, and we'll be able to set these up. And then you can do all kinds of fun things, right? I could get 3 of these in there. So that's a wavelength and a half. Or I can get 4 in there, which is going to be 2 waves and a half. And anytime that I get that fixed point, I'm going to be able to set up a standing wave. So this would be like a wave in a string, like the waves on a guitar, or the waves in a harp, or the waves in a piano. Okay, I'm going to be able to set those up. But we also know musical instruments do some other things. Musical instruments, and we've all done it, right? We've all done it. I can do a pipe. So there's my pipe. Now I can't set up a node at the end of my pipe. I can only set up antinodes at the end of my pipe to get harmonics. So this one, if I do this, I'm going to get, there we go. This is still only half a wavelength because I'm going from antinode to antinode. Okay. But I'm setting up my antinodes at the open ends of the pipe. Now, what happens if I have a closed pipe? So this time I've got a closed pipe. I'm going to get my antinode at my closed pipe, or my node at my closed pipe in. I'm going to get my antinode at my open pipe in. I'm only going to get a fourth of a wavelength. So this is both open ends. And this has an open and a closed end. So I can set up those nodes and those antinodes as I go through and look at a variety of different pieces. So I can get those things that are happening. So that's so if I'm dealing with standing waves, and so when we come back and look at the mathematics, we can play with that going forward. All right. So we talked about questions about standing waves. Again, we're just doing them conceptually right now. Okay. So let's talk a little bit more about sound waves. Let's talk about, because that's what we're really trying to get to is sound waves. And we're trying to get to how things are going to work. So one thing that we want to look at is on a string, I'm confined only going up and down the string. So on a string, I'm only confined there. But sound waves are longitudinal waves. We're going to get that compression or that rarefication, compression, rarefication, compression, rarefication. So if I'm looking at a speaker, so here's my speaker, right? There goes my speaker. And this, my little magnet is going to vibrate back and forth on my speaker. And what we'll do is we'll see a thick area. My little air molecules are going to be really, really thick. And then they're going to space out. And then they're going to be really, really thick. And then they're going to space out. And they're going to be really, really thick. And we can represent this as our wave. So we can still use our simple harmonic motion to deal with the wave. But our sound wave doesn't stay like that, right? Our sound wave doesn't stay like that. So we can describe this as a wave front. So we can use an arrow and say that this is a wave front. And what's interesting about a wave front is if I'm looking at, so let's take our water wave here. So we've got we've dropped our pebble into the water, and we're going to come to a gate, right? We're going to come to a gate, and we've seen our water do this, but what happens? If I have a block, all of a sudden my water's going to do that. So each point on my wave front can be a source of another wave. Pretty cool. That's a principle we're going to see a couple of times. And that's going to be a principle we're going to see in light waves as well. But as I go through here, I start seeing this. And this, of course, is representing our wave front. This line here, we're using that to represent how that wave is going to move through. But let's go back and let's look at our sound wave. So I have a sound wave. Okay. We're going to go out here. We're going to send our little speaker out here. and we're going to look at the sound wave, it's going to go out and it's going to travel away from my source. And if we call that a source, what is the source of the sound? Is it my speaker? Is it my mouth? Is it something like that? If we do the source, it's going to move away. And if I have all of my energy in my sound, so let's think about all that energy. So I have my explosion, right? I got my explosion and it bursts, and my explosion bursts. We know right up close that the intensity of that is pretty strong. It's going to be very intense right next to it. We also know that if we stand next to a speaker, right? So those of you who go to rock concerts and go to everything, if you're up in the front row and you're standing by the big speakers and you're feeling the vibrations through your whole body, and it gets loud and you're experiencing it because you can feel that intensity of that speaker putting out that energy. Because remember, waves carry energy. You're putting out that speaker, that energy. And if you're standing right next to it, it could be almost unbearable. But if I step away from it, I don't feel it quite so much. Same with the idea of if I'm in a refinery or if I'm in some kind of manufacturing facility, if I'm right up next to that piece of equipment, I hear it and it's loud. It's way loud. But if I go stand over on the other side of the room, it's not so loud. We actually see this decrease because if I look at this wave front, that energy of that wave, what's happening to it? The surface area is getting bigger and bigger and bigger as it goes out, right? My surface area is getting bigger and bigger and bigger as it goes out. This is also spherical. I've represented it as a circle on the screen, but we know it goes out like a big balloon. It goes out like a big balloon and it gets out and it goes spherical, 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 spherical. Okay, goes out. Well, what happens as I move out from here to here? If I look at this one, the intensity at this, if I'm spreading it out over the entire sphere, what's the surface area of a sphere? Surface area of a sphere is 4 pi r squared. Okay, surface area of a sphere is 4 pi r squared. As I move out here, my r is getting bigger. So my intensity actually falls off. So if I do a plot of intensity versus distance, my intensity versus distance falls off, and it falls off as 1 over r squared. Falls off as 1 over r squared. One of the laboratories that you guys are going to do, and if you think about it, also on if it's clear, okay, sound's going to travel really, really well on a clear day. It's not going to travel so good or so much during the snow. Snow actually has a deadening effect. Snow actually gives us constructive interference. But if you think of it, that makes sense, right? If you think of it, that makes total sense because I can get reflection of my sound. So if I'm coming up, what we didn't talk about, if I take my pulse and it hits a fixed spot, okay, it hits a fixed spot on the string and this is fixed, I'm going to get the pulse. So this is the pulse going this way and this is the pulse going that way. It's going to reflect off and it reflects. And we know that because these are particles, right? So if I take a ball and I throw it towards the wall, what happens? It bounces back. It comes right back to me. It bounces back. I get a reflection. Waves are energy. Waves are particles. So if I send the wave out and I push that wave front towards the wall is going to turn it around and have it come right back to me. It's going to reflect that wave. It's going to totally reflect that wave. So we're going to get that reflection. Well, what happens when it's snowing? when it's snowing, I got a whole bunch of little things out there that the waves are going to hit and they're going to disrupt the wavefront. And if they disrupt the wavefront, I get more chances for reflection. I'm going to get sound deadening, which is why your sound walls, if you go into a room that's been put in for sound deadening, you're going to find that the walls have those kind of egg cup shapes on there. Because what it's trying to do is as the sound hits the wall, comes back, and if I break it up against the wall, I'm going to get more of that reflection. I'm going to get more chances for destructive interference. Even in a symphony hall where we're constructing the symphony hall to get constructive interference, there are still places in the symphony hall that are going to be deader than a doornail, because we always are going to have a place where the interference is going, or the things are going to cancel each other out. So we try to minimize those dead spaces in a concert hall. We try to maximize those dead spaces when I'm trying to get a silent room. So those are things that we deal with. But as I'm moving away from my source, and we're going to talk about intensity being the source, we're going to move away from that source. It's going to fall off as 1 over r squared. And we're going to do an experiment to show that. And basically how that experiment works is you're going to find something that has noise associated with it. Could be today, it could be a heater. It could be a fan. In the summertime, I tell them get outside and listen to your air conditioner, your compressor on your air conditioner, and go outside and do that there. And stand about 1 meter away, and you can use your Firefox app. There's a sound intensity, or there's a couple of other sound apps, and we'll talk more about that on Monday because I'll describe this experiment on Monday as well. We'll do that sound app, and then you go, so you'll be about 1 meter away from whatever your sound source is, and then travel about 10 meters away, and then measure your sound source again. I suggest that you do it outside because rooms give you interference because the sound's going to bounce off the walls. So you still can do it inside of a room, but you have to be aware of that interference and know that that's what you get. I did it with a compressor station at my house, and I measured it about 10 meters away, and then I measured it 1/4 mile away. And man, you can see this graph, and this graph comes up really cool. As you can see it as 1 over r squared. All right, I'm going to stop. Other questions?